Lesson 26, Parametric Descriptions for Oriented Curves. In this lesson, we're going to be talking about some of the strategies that you are going to see implemented on the examples in this lesson, where all the examples here are going to try to take either a set of parametric equations involving a variable t, and trying to convert that back into a Cartesian equation. Or you will see a Cartesian equation that is defined as either a function of x or a function of y, and we're going to try to parametrize that to convert it back into a set of parametric equations. Now I will say up front, there is not much of a purpose of converting parametric back into Cartesian. Most of the time, if you have something in parametric curves, there's a reason for that. And it usually is the fact that you don't want the entire curve, but you just want maybe a section of it. There is going to be purpose, though, to convert from Cartesian to parametric. That actually is a little bit more common. As I had just said, because we are very commonly going to take portions of a curve, which parametric is really good to define. And also, if we want to make sure that we are defining a specific orientation, if we're trying to go from one point to another. You are also going to see a couple examples where some graphs that are in parametric look a little bit better when they are in parametric, or look a little bit easier to solve, rather than if they're in Cartesian. Overall, to convert a set of parametric equations into a singular rectangular or Cartesian equation, we can simply isolate the parametric variable t in either equation and substitute into the other to eliminate the parameter. That is going to be one of the main strategies. Take a set of parametric equations, solve for t in one of them, and then use that to substitute into the other. If, however, you're converting an existing Cartesian equation into a set of parametric equations, that can be done in a few ways. If you have y equals a function of x, for example, y equals x squared plus 2x, then just replace x with t, and then you have y as a function of t instead. For example, if I have y equals x squared plus 2x, as I said, we can just say we'll call x t because it is the dependent variable. And then we'll define the independent variable y as now t squared plus 2t. Congratulations, we have currently parametrized this. Again, the main reason why you would want to do that is if you don't want the entire curve of x squared plus 2x, maybe you only want a portion of it that's defined for 0 to maybe 3 or something. That would be a purpose as to why we would want to parametrize that. You could do the same thing if you have x as a function of y. Define y as t and then replace all instances of y with t to get a function for x. The more interesting cases that you'll see here involve 3 and 4. The third one here says to parametrize a line segment defined by x0, y0 to x1, y1. You can let x equal x0 plus x1 minus x0 quantity times t, and y equals y0 plus y1 minus y0 quantity times t. This should look a lot like the slope-intercept form formulas, and that's basically what it is. We just want to think about what points are we starting with x, and how much do we need to change to get to the next. If you're parametrizing a function that is x minus h squared over a squared plus y minus k squared over b squared equals 1, which is the definition of an ellipse, unless a and b are equal, in which that's a circle then. As long as a and b are greater than 0, you can let x equals h minus a times cosine of t, and y equals k plus b sine of t, for 0 to 2 pi. What that essentially means and where that's stemming from is we're going to relate that equation of something squared plus another thing squared equals 1 to an equation that we've had far in the past, which would be cosine squared plus sine squared is equal to 1. If I can relate this first piece to cosine squared, and I can relate the second piece to sine squared, then I have a way of parametrizing both x and y. And the results that we get are relatively simple looking functions. Furthermore, the results we get, x and y, are themselves actually functions. Whereas this equation, which is trying to make an ellipse or a circle, is by definition not going to be a function on the Cartesian plane.